Welcome to lecture 21. Today we'll talk about another application of the Bernoulli equation, and this is a nice example called the Pitot Tube. This only works if you have a steady flow, and also it has to be irrotational and constant density. And those are your standard requirements for the Bernoulli equation to hold. The Pitot tube can be used to measure the velocity of wind in a duct or a current in a duct. It can also be attached to a ship, and then if the ship's going at a steady velocity relative to the water, you can use the pressure in the Pitot tube to infer how fast the velocity of the ship is. Here we'll look at a particular setup with a flow in a duct where you have 2 points. So let me just sketch this out. So we'll consider 2 points here. The first one being upstream of the Pitot tube. This here is the Pitot tube. And there's an opening at this point x1, and then the second one being right here in front of the Pitot tube, right at the opening of the Pitot tube, and that's going to be x2. And these two lie on the same streamline. So we have a streamline here, and as we know that along a streamline, the Bernoulli function is constant. So u squared over 2 plus gz plus p over rho, which is b, is constant. So how does that help us in determining the velocity of our flow? Well, so we assume that we have constant velocity u coming in here. So this is u, and that means that at x1, u of x1 is assumed to be upstream enough of the Pitot tube that it won't be affected by having that that obstacle in there. So that's just going to be u. U of x2, since this is right here at the edge of the Pitot tube, and the water in the Pitot tube has to be stagnant, right? There can't really be any flow in here. So u of x2 is 0, and that's also, x2 is therefore called the stagnation point. We can then write our equation here as Bernoulli at x1 has to be the same as Bernoulli at x2, since both points are on the same streamline. And Bernoulli at x1 is just u over 2 squared plus gz plus p at x2 over rho. So p of x1, right? And let me backtrack here. This is u of x1 squared, which is just u. So u of x1 squared plus gz plus px1 over rho has to be equal to u of x2 squared over 2 plus gz plus p of x2 over rho. Now, this term is 0, since u of x2 is 0, and these two terms cancel, since both x1 and x2 are located at the same height. The pressures are going to be different at x1 and x2, and they will depend on the overburden here of the water column. And so if we call this h1, then the pressure at x2 here will be the same as pressure at this point. And so let's call this distance h2. Now, once we've cancelled the terms down here, we can rewrite this as u squared over 2 plus px1 over rho is just px2 over rho. And then we will solve this for u, and we find that u is the square root of 2 over rho p at x2 minus p at x1. The nice thing is that we know what these two pressures are going to be, and so if you think back to the manometer from a few weeks ago, we realized that the pressure at x1 is just the hydrostatic pressure there. So it's the weight of the water column, rho g h1. And the same holds for p at x2. P2 is rho g h2. And there might be, an atmospheric correction here because there's a atmospheric pressure at both terms. But that is the same for both, so we can just ignore those. So let's plug P1 and P2 in my equation 1 here. Plug into 1, and we find that u, the velocity in our duct, or if it's an open ocean and this is attached to a boat, the velocity of the boat is just the square root of 2g h2 minus h1. And so if you can measure this distance here, d, that's typically the only thing that you need to measure if you have an open surface. And then you can infer how fast your flow is, or how fast your boat goes. And that is the concept of the Pitot tube.